Okay, so this video is in response to some of the questions that I've been getting. And the first question that people have been asking me is why this option A is an infinite amount of triangles. Okay, so specifically in this case, let's say we have a triangle that has 100 degrees in one angle, and then another one that is 30 degrees, and then obviously the one that's left is 50 degrees. So why can there be infinite amounts of triangles with these three measurements? Because you can just have something that is proportional to this, and the angle measurements will be the same. In this exercise, you're not asked to prove that, so you don't really have to do any proof. Just understand the fact, and you can see that easily. We could just replicate a triangle exactly like this one, but a little bit larger, and then necessarily the angles would be the same. And this can go ad infinitum, so that is the reason why. But if you had to do a proof, then one idea would be to do something like this. First, let me get rid of this. Let's just draw a triangle. And in this case, we're going to call the vertices A, B, C. And then we call the sides with a small cap letter A, B, C. And let's grab just one of the angles, and you could do the same with all the angles and use different names for the angles, but just in this example, I'll use one. So what we know to be certain from the law or rule of cosine is that side c squared is equal to a squared plus b squared minus 2ab cosine of c. This is already proven, and we can base a proof that we would find infinite triangles that have the same angle measurements by repeating this process with all the other angles if you want, but should suffice with one, because if it's true for one, it's true for all the other proportions, or all the other sides. So because this is true, we could apply that to, say, another triangle that would be proportional to this one. So let's just multiply all sides by k being any, let's say any number belonging to 1, 2, 3, etc., right? So natural numbers. K belongs to the naturals. And if we applied the same rule, we could say then that K times C, or KC squared, should equal KA squared plus KB squared minus 2AK BK cosine of C. And then you can expand that, and you're going to get K squared C squared equals K squared A squared plus K squared. I think you get the idea. If you K squared B squared minus 2K squared AB cosine of C. And then you could factor out K squared, and you get an expression that says something like K squared times C squared equals K squared times A squared plus B squared minus 2AB cosine of C. So then we can cancel out the K squared, and we can see that this expression is equal to this one. So that means that for any K, this holds to be true, and the angle measurements would be the same. Because if you recall, to find the angle would just be using the inverse cosine of the same expression, right? If you remember that the inverse cosine is simply rearranging the equation, so it would hold true for any angle. You can multiply everything here by k, and then get k squared, and cancel out the k squared as well. So the next question that people have been asking me about is number 3, where they ask us to find the lengths of the diagonals of a parallelogram whose sides measure 14, 18, and has one angle with measure 37 degrees. So recall that if you have a parallelogram, it looks a little bit like, let's say, something like this. Excuse my drawing skills here, please. Let's say it looks like this. If it's a parallelogram, then the sides have to be parallel in pairs. Okay? So I hope that looks like a parallelogram. And they say that one of the angles is 37. So if one angle is 37 degrees, that means that the other angle, the opposite to this one, has to be 37 degrees. But not only that, these other angles are also predetermined, and they're also the same. Otherwise, you wouldn't have a parallelogram. And this angle here has to be equal to 360 for the whole sum of all the angles, minus 37 times 2, and then the result of this split in 2 because we have two angles, and that is 143 degrees. So this would be 143 degrees. Then we think about the diagonals, but we can think about the diagonals as being triangles, because we can find one diagonal using this angle, and we can find the other diagonal using the other angle and using the rule of cosines, because they tell us that one side is 18 and the other side is 14. So then the full length of, let's say, this diagonal here would be applying the cosine rule with this and this, and then finding the other diagonal, which is this one. We could do a similar process using, again, 18 and 14 here, and using this angle. I hope that clarifies, and I'll leave it there so you guys can finish. Okay, so here's another question that I've been asked about, and it says that the lengths of the sides of a triangle ABC are x minus 2, x, and x plus 2. The largest angle is 120 degrees. Find the value of x. Maybe some of you missed this little x here and didn't realize that you had a triangle, obtuse one, by the way, because, well, that doesn't look obtuse. Let me do that again. So let's do an obtuse triangle, and it has 120 degrees, and it says that those are the sides. Now, obviously, the longest side has to be opposite this large angle because the triangle is obtuse, so this side has to be x plus 2. Then we can just pick the shorter side to be x minus 1, and the one that's between to be x. And then if you want to find the value of x, as part A says, all you have to do is use the law of cosines. So you can set it up on your own. This is all I'm going to do here, because then the rest will be easy for you after you understand this part, right? Because this would be this x plus 2 squared equals x squared plus x minus 1 squared minus 2 times x minus 1 cosine of 120. So I'll leave it there, and I think that you guys can take it from this point on. Okay, so the next problem that people have been asking about is number 12. And it says, let A, B, C, the sides of a triangle where C is the longest side. If C squared is greater than A squared plus B squared, then what is true about triangle ABC? And then B is the same, but with C squared less than A squared plus B squared. So let's think about the case where C squared is equal to A squared plus B squared. And that case is the one we know very well from the Pythagorean theorem. If this is A, this is B, and this is C, then this would hold true. C squared would equal A squared plus B squared. But what happens if we have a triangle that is actually here, where C was obviously going to be smaller, right? In this case, we know that C squared would be less than A squared plus B squared. And the other case is where this is actually larger than this C. So C squared would be greater than a squared plus b squared. So intuitively, this is pretty obvious. But how can we prove it using the cosine rule? So let's do that next. So the cosine rule says that c squared is equal to a squared plus b squared, which is the Pythagorean theorem, right? Minus 2ab cosine of c. So the first case, let's use the first case, and this is when c is equal to 90. Then if c is equal to 90, cosine of c would be equal to 0. So then we would have the same expression, c squared equals a squared plus b squared, the Pythagorean theorem. The second case is when c is, let's rewrite this here for a second. When c is actually going to be less than 90, so c would be less than 90 but greater than 0. So then cosine of c would be a value that would be less than 1 but greater than 0. Remember that cosine, so that means that in this case cosine of c would give us a positive value because it's between 0 and 1. Now if it's positive, that means that this expression here would not be affected by this, so this would be negative. Therefore, c squared would be less than a squared plus b squared. And you might ask yourselves, why? Why would it be less? Well, because if c squared is equal to a plus b squared minus this, it means that the only way for c squared to equal a squared plus b squared would be if you add 2ab cosine of c. Then this would equal a squared plus b squared. That means that this is equal to that. So that means that c squared must necessarily be less than a squared plus b squared. And similarly, for the third case, because in this case, when the angle C is greater than 90 but less than 180, then cosine of C would be less than 0 and greater than -1. And obviously all of these are negative, so that would make this positive. That would make this positive. Therefore, c squared would be greater than a squared plus b squared. Okay, so here we are on the final question, which is 16. And it says that in triangle PQR, QR equals P. So QR is P. Let's write it here, small cap P. It looks like a capital P. So I want a small cap P here. R is here, and all of this would be Q. Notice that it's just the same notation that we always use with triangles, where the vertices are capitalized and the opposite sides have the same letter but small cap. So in A, they ask us to show that RS is equal to Q minus R cosine of P. Well, by looking at the triangle itself, we can see that RS is equal to Q minus PS. So what they're really asking us is to write PS in terms of cosine of angle P. Now, if you look at angle P, you know that cosine of angle P would be equal to PS divided by R. So that means that PS is equal to R times cosine of P. Therefore, RS is equal to Q minus PS, or Q minus R cosine of P, as we wanted to show. Then in part B it says, hence, by using the Pythagorean theorem in triangle QRS, prove the cosine rule for PQR, triangle PQR. Okay, so that means that they want us to use this for RS. So let's write it here. RS would then be Q minus R cosine of P. And they want us to use Pythagoras theorem to prove the cosine rule. Okay, so the only way we can relate two triangles here is by using QS, the height, because QS is the side that is common to both triangles. So let's put two equations in terms of QS. So QS squared, which is a leg, would equal hypotenuse squared minus the other leg squared, minus PS squared. But we don't want to introduce PS here. We can use instead an expression which would be R cosine of P. So let's use this instead. And then we know also that QS squared. Now this is not just the S squared. I'm squaring QS entirely, just so we don't confuse anything here. So QS squared from the other triangle would equal the hypotenuse P squared minus RS or SR, but we're just going to write Q minus R cosine of P squared. Okay, then from these two expressions, because they both equal QS squared, that means that they're equal to each other as well. So that means that we can rewrite this and say that R squared minus R cosine of P squared has to equal P squared minus Q minus R cosine of P squared. Okay, so this is where we're going to prove the cosine rule for PQR. And we can do that by expanding these expressions. So we're going to get here that R squared minus R squared, because these two are multiplying, R squared cosine squared of P is equal to P squared minus Q squared minus 2QR cosine of P. I'm going to erase this so I have more room. Cosine of P plus R squared cosine squared of P. Okay, so there's a negative in front of all this, so that's going to change all the signs, right? That means that this will be negative, this will be positive, this will be negative. Yeah, I'm going to just rewrite that to avoid confusion. So this will be negative, this will be positive, this will be negative, right? Okay, so once we have that, we can see what terms we can cancel out. And obviously we can cancel out this thing. And then with this, we can rearrange the equation. How so? Well, look, we have that this is positive. Let me rewrite it so that it's clear. This is positive. This is gone. This is gone. So if I keep P on this side, I can write this as P squared equals R squared. Now this will be plus on the other side, so plus Q squared minus, and I'm going to reorder this for sake of clarity, so 2RQ cosine of P. And this that we have here is the cosine. And that proves it for the triangle. Because if this is true for one of the sides, it's true for the other ones. Then, for part C, I'm going to erase everything on the board here so we can continue with part C. Since we already proved that the cosine rule is true, we can now do a different problem. And here, what they're asking us to prove is that we can use the cosine rule for this, to show this, giving us the angle PQR. Okay, so since we have PQR, let's mark it here. They're giving us this. So we know that this is 60 degrees. Now everything we're going to do has to be in terms of P, Q, and R in small caps. So remember that this side is Q, this side is P, and this side is R. So simply using the cosine rule, we know that Q squared is equal to P squared plus R squared minus 2PR cosine of 60. Okay, so let's simplify this because cosine of 60 is 1/2, right? So cosine of 60 is 1/2. That means that this will cancel out here. Then we can rewrite that. We're going to have Q squared equals P squared plus R squared minus PR. So let's look at this expression. And maybe you guys got to this point, which would be great, fantastic, because then you're just missing something very little. Now, what does this answer look like to you? The plus minus, a square root with terms subtracting, a 1/2. That could also be dividing by 2. Doesn't it look like the quadratic formula? Well, that's what it is. And we have to solve for P. So let's reorder this here. We can rearrange this and rewrite it as P squared minus PR, or RP. Let's write RP just for sake of clarity. Plus R squared minus Q squared is equal to 0. So if we look at this as a quadratic, this would be the first term, this would be the second term, and these two would make up the third term as a constant, right? Because we're solving for P. So that means that A is 1, B is negative R, and C is the expression R squared minus Q squared. And then we can use the quadratic formula to solve this. As we know, the quadratic formula says that the solutions, in this case, for P, right, would be in the form of minus B plus minus square root of the discriminant, B squared minus 4AC over 2 times A. So let's substitute all that in there. And we're going to get minus R, so that'll be R plus minus square root of B squared, so that would be R squared minus 4 times A times C. C is R squared minus Q squared. All of this over 2A, and 2A is just 2 times 1, so 2. Okay, so we're almost done here. So notice that we can rewrite this as 1/2 times R plus minus square root. And here we go, R squared minus 4R squared plus 4Q squared. And then we're practically done because all we have to do is simply rearrange this in here and we'll be done. So that this is equal to 1/2 R plus minus square root of 4Q squared minus 3R squared, as it asked us to show or prove.